All right, so we just finished having a look at one-to-one functions, and we're going to have a look at an example now. So let's have a look. So consider the function of x equal to 2x plus 3. So this is the notation we were talking about last time, and it's the same as f of x equals 2x plus 3. Okay, just another way of writing it, and we're just going to get used to that. All right, we're not to worry too much about it. It looks complicated, but just what we're doing now. So on the same set of axes, graph f and its inverse function, inverse function f to the negative 1. Okay, so we also remember that in our last video we discovered that f to the negative 1 of this function was equal to x minus 3 over 2. Okay, so we're going to graph those on the same set of axes. All right, so what I've got here is the graph y equals 2x plus 3. You can see that here it's just a standard straight line, linear equation. And if I turn on my graph, I'm just using Desmos, and I've graphed the inverse function here. Now, it doesn't look that special at the moment, just those two. But if I turn on my y equals x, remember we have to be symmetric around that point. So it's kind of like a mirror. You can see over here we go through the point 0, 3. Down here we go through the point 3, 0. Okay, so it's symmetric. You know, if we can pick any point on the graph here, and they'll be opposite, you just change the x and the y. Okay, so that was the first part. And just a good look at what an inverse function actually means. This is what happens with all of them. Okay, so we've done part A. We had a look at that, and hopefully we saw what happens there. Now, what we've got to do is we've got to find the inverse. So we've done that previously, and we use that variable interchange method. I'll do it again just to refresh it. But the other thing we can do it with is using coordinate geometry and the gradient. Okay. So what we're going to do is, we'll start by finding the gradient. So what we're going to do is we are going to have a look at f of x. So from our graph, I saw that f of x passes through 2 points, 0, 3 and 2, 7. Now what that means is our f of negative 1, our inverse, that passes through the opposite, so 3, 0 and 7, 2. Okay, so if we want to find our gradient is our rise over run, or our y2 take y1 over x2 take x1. So let's have a look. We got our y2 is 2, take away our y1 is 0, 2 takes 0, divided by our x2 is 7, minus our x1 is 3. So we can get 2 take 0 is 2, divided by 7 take 3 is 4. 2 over 4 equals 1/2. All right, so that's the first part. So that's going to be our gradient. We know it has to be a straight line, and that's going to be our slope or our gradient. So the other thing we can do is substitute in those x and y's. So what I'm going to do is I'm going to go back to this equation, my gradient, but instead of the 2 and the 7, I'm going to put in my x and my y. Okay, remember the top row is our y's. So I'm going to change that 2 to y, so y minus 0 divided by x minus 3. Okay, and that equals my gradient, 1 over 2. So now I times both sides by x minus 3 to get rid of that on the denominator. So y take 0 is just y. Y equals 1/2 times by x take 3, and make sure you times the whole thing. Okay, and what we're going to get there is if you times the whole thing by half, you get y equals x minus 3 all divided by 2, and that's what we got originally. Okay, so this is the coordinate geometry and gradient method. All right, We'll have another look at the variable interchange method as well. So for me, the variable interchange method is just a little bit quicker, but whatever you'd like to do, that's fine. So we start with y equals 2x plus 3. We substitute our x and our y. So we change that to x equals 2y plus 3. And we just try and get our y back to the start. So the first thing we do here is remove the 3 to the other side. X minus 3 equals 2y. And then divide both sides by 2. So if we divide that by 2, that goes away. Have to do the same thing to the other side. I'm left with y equals x minus 3 on 2, and I get the exact same thing. All right, now we've done A, B, and we're up to that last one. So let's have a crack at that now as well. So I'm just going to have a go of that just over here. So I want to do f of my inverse. Okay, so I've got my inverse here, and I've got my original equation here. So what I'm going to do is just substitute that in. So I've got 2. So I'm just going to write. I'll write y this time just because y equals 2 times my x. So this is now my x. X take 3 over 2 plus 3. So 2 and then divided by 2, they're going to cancel out. And I'm left with just the top there, x minus 3 plus 3. Minus 3 plus 3, I'm just left with y equals x. All right, and that's what I was supposed to be left with. Now the other way I can do it is I get my inverse function and then chuck my regular function in there as well. So this one is here. I'll just box that off as well. So take my inverse, x minus, I forgot again, let's just use y. X minus, oh, bad mistake. So f of x equals x minus 3 on 2. Now my x is up here, so change my x to 2x minus, 2x plus 3. That's this one here. Put it in for here. Minus 3 all over 2. Now I can open those brackets up. I've got 2x plus 3, take 3 over 2. 3 take away 3 is 0, so I'm left with 2x plus 0. Don't need to write that. Divided by 2. 2 divided by 2 is 1. I'm left with f of x equals x. So I've proved that for this one here, and for this one over here, that it works out. Now I'll have a look at one more thing, mainly because it's cool. So the sine x and its inverse. So if I have y equals sine of x, and I use the variable exchange method, so x equals sine of y. The way I remove my sine from this side and take it to that side is I have to go arc sine to both sides. So arc sine of x to this side equals arc sine of y. Now these two are like opposites, so they're going to cancel out, arc sine and sine, and I'm left with my y. So y equals arc sine x. Okay, so that's just a bit of play around with that. But it's really cool when you have a look at the graph of these. Okay, now if we draw our sine of x, we all know what that looks like. Now if we draw our arc sine of x, we can see that this is forming, if I put my y equals x in there, it forms like a mirror image around that, except it stops here at this point, pi on 2 and 1. Okay, now that's because the reason it stops at 1 and -1 is because you can see here, that is our range on our y, because we can see that's our domain on our x. It stops at -1 and 1. That's because our range on our original function, the lowest it can go to is -1, so that had to match with this -1, and the highest it went is +1, which matches with this +1. So they've swapped. So highest y value has become the highest x value. Now it's weird because this one repeats over and over again, and this one doesn't. That's because if we use the horizontal line test, you can see we'd hit, if I went across here, we'd hit here, 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 here. We'd hit everywhere. So we can only look at one half wavelength to do that. And our half wavelength stops at negative pi on 2 at the bottom and positive pi on 2 at the top. So those were our x terms, but they become our y on our inverse graph. So that's cool. That's just using the facts that we've got. Yeah, hopefully, yeah, kind of makes sense after what we talked about. All right, thank you.